There you go. Right. Yes. Okay. Devel NYTProf. Source code profiler. Has anyone used Devel dprof recently? Would anyone be tempted to use Devel dprof? Okay. Cool. Because basically it's completely broken. Generate 1,000 subroutines that are all identical, profile them, and Devel dprof says that all the time is spent in 4 of them. Because it has a very slow clock, and what happened was those were the 4 that were executing at the time the clock ticked. So the faster machines get, the worse dprof is broken. Okay, bit of profiling. You want to know how fast things are going, but do you want to measure CPU time or real time? And do you want to measure by statements or by subroutines? Okay, so let's look at the subroutine statement axis first. For subroutine profiling, you're measuring the time between entering a subroutine and the time you return. And we call that the inclusive time. That's all the time you spent in the subroutine and whatever the subroutine called. And it's reasonably fast, and the exclusive time you get by subtracting the inclusive time of the things you called. I'll show you that later. So it's reasonably fast for profiling, and that's why most profilers that you've probably used before do subroutine profiling, because the profiler only gets involved when you're entering and leaving subroutines. But a lot of the old profilers would get very confused by funky control flow, like a next or a goto out of a subroutine. And for big subroutines, knowing how much time was spent in there doesn't shed any light on where the time was spent within the subroutine. And also, if you've got a script, you might have a big Perl script that has no subroutines at all, and then you get no insight whatsoever. Now, from a statement perspective, what you're doing is you're measuring the time from starting to execute one statement to when you start to execute the next statement, wherever that might be. And that might be somewhere completely different. So if you're calling a subroutine, it'll be the first statement of the subroutine you've called. If you're in a while loop, and you've finished the loop, it'll be the next statement that you execute when the control flow flows back to the beginning of the loop. And that particular case has caused some problems for some old statement profilers. But the great thing is you get a lot of detail. You get to see the timing of every single statement. But the problem is the profiler is involved all the time. Every single statement the profiler is involved. So it's very expensive, which is why there haven't been many statement profilers in Perl before. And also, when you kind of look at a whole big script, a whole big program, there's too much detail. Yep. You really need to see subroutine timings to get a sense of where to focus on, and then statement timings within those. Now let's look at CPU time and real time. Who would prefer to measure CPU time? Yeah, you've seen this talk before. And who would prefer to measure real time? And who isn't sure? And who has no hands? Okay, so CPU time, sort of traditionally benchmarking was all done about CPU time, and that measures the time that the CPU was executing on your behalf. So it isn't much affected by what else the system's doing, but it doesn't include time spent waiting. Time spent waiting for I/O, time spent waiting for networking, time spent waiting for the CPU, time spent waiting for memory, cache misses, the whole shebang. But real time is wall clock time. You know, you're waiting in real time. You're not waiting in CPU time. So it is affected by the load on the system, but it includes all the things you're waiting for, all the things your program's waiting for, the CPU, network, database, memory, locks, the whole shebang. So real time is really what you should be measuring. The only time you want to measure CPU time is when you're actually benchmarking the CPU efficiency of a particular piece of code. And that's not what profiling is about. So, Devel NYTProf. Public service announcement. The name is an accident of history. I do not work for the New York Times. I have never worked for the New York Times. I have no affiliation with the New York Times whatsoever. The New York Times last contributed in 2008. So the number of times I get asked, what's it like to work at the New York Times? Okay. Now, having cleared that out the way, so how do you run it? Perl-D, I'll give you a little example later. You can also just load it as a module, and it'll do the right thing. There's also lots of other ways of getting it loaded, and this one at the bottom is particularly useful. If you have Perl code that is being fired up by some other process, and you want to profile it, but you can't change the command line, if you set the Perl 5 opt variable to the -d NYTProf, and then set the NYTProf variable. Hey, I have a pointer, and do this add PID. Then any Perl scripts that get executed under that, while these are set, you'll generate nytprof.out with the process ID of the file, of the process added. So you'll end up with a collection of profiles, which you can then go and look at and analyze. I've not used this myself, but one of the things you can do with the data file that gets generated is run kcache grind, which looks really cool. It's part of the Unix performance tuning suite, you might say, and it generates this. I've not used it myself. It's probably very good. It looks like it ought to be very, very good, but I can't say more about it because I haven't used it myself. What you're most likely to use is the HTML output. And that generates a nice HTML report with one page for every source file, plus some summary pages and visualizations. And this is what it looks like. So this is the index page, the sort of top-level view. Actually, this is a bit old because there's now a flame graph on there. Yeah. Okay. So you get a summary, the time you generated the port, the time it was run, how long it was spent, what it includes, and links to the source code. This is the kind of the subroutines that had the largest exclusive time value. So it just shows you the top 15. And there's a link at the bottom to you go and see all of them. And it tells you when you've got X subs or opcodes. Now, just on that previous slide, you've got exclusive time and inclusive time. So I just want to explain a little bit about that. So you're running some code and you call a subroutine, and the subroutine spends a little while and then comes back. That's your inclusive time. But if that subroutine calls another one, not recursive calls, nested calls. Okay, so the way I think about inclusive versus exclusive is that inclusive time is best for a top-down view of your application. So the traditional example is you might have some code that spends a chunk of time loading data, spends a chunk of time manipulating data, and then spends a chunk of time spitting it out. So the inclusive view from the top down would show you, well, how much time do I spend loading? How much time do I spend manipulating? How much time do I spend spitting out? Yeah. So it's a high-level view. The exclusive time is more bottom-up. It's showing you the time spent in the subroutine where you're actually executing the statements in that subroutine, not in some other one. So it's very much a bottom-of-the-tree view. Okay. Now, when you click on one of those links to look at a particular subroutine, you'll see something like this. Up here, you get a summary and one line for each different place that called your code. Each different location in the source code that called into this subroutine gets listed here. And also within the subroutine, every statement that calls out somewhere else, you get a summary of where it was called and how long it spent. The first two columns here is the number of statements executed, in this case just one, the time spent on that line, the number of calls made, and the time spent in subroutines, which is, that's what that says. There you go. You could read that. Okay, but and then a tree map. Now the colors are awful, and I apologize for the colors, but that's a long story. The colors don't mean anything other than to group related packages. Yeah, so ignore the particular colors used. What's happening here is that the boxes of the tree map represent the time spent, the exclusive time spent in each of the subroutines. The bigger the box, the more exclusive time. Okay, and I'll give you a demo in a sec. You can also generate these nice graph viz diagrams, and they look really cool and lovely. And yep, there's another one. So this is a sort of inter-package view, and this is a subroutine view. Really, I might remove this because for any program big enough that you want to profile it, it's just insane. Graph viz will spend like weeks generating this, and you'll end up with just something. It's just a mass of lines and bubbles, and it's a complete. But it looks good. Okay, ready for a demo? Has anyone not used NYTProf before? Ooh. What have you been doing? Okay. Okay, so my traditional use case here is running Perl Critic on itself. So here's Perl Critic running on its own source code, or a little bit of its own source code, takes about 1.5 seconds. And here I'm going to run it with Devel NYTProf. And it takes about 6 seconds. It's about 4 times slower than the code normally runs, which is pretty good, really. And then we generate a report. And that's reading the data file generated by the NYTProf. And here I gave it the open flag, so when it's finished, it'll just pop open the browser. Here is extracting the subroutine call data, and there were lots of them. And we use that to generate a flame graph that I will show you in a sec. Kabam. And here is a rather nice visualization of Perl Critic. So we have up here the time it was generated and how long it spent executing so many statements and so many calls and so many source files, and you can jump to a particular source file if you want. But really, this is rather lovely. This visualization, the flame graph, was developed by Brendan Gregg. I think I'm pronouncing that correctly. And it's a lovely way of visualizing very quickly where the time is being spent. The colors are not meaningful, and the position on the x-axis is not meaningful. What's happening here is every distinct call tree is a slice of this diagram. If you can imagine turning it sideways and slicing it up, every distinct call tree is a column on this diagram, and then it's stretched out according to the amount of time spent in that particular call tree. So a particular subroutine may turn up in multiple places in this tree, depending where it was called. And as you browse around, you can see the time. So down the bottom here, this is kind of the complete time for the script, and then almost all the time spent in run, critique, and then there's a big division here. This is all the begins. So this is your Perl Critic begin, and these are your begin blocks. And so this is kind of all your load time stuff. Everything's being loaded and got ready. And then over here is Perl Critic running itself. What's this one? Perl Critic, yeah. So that's the one over that I showed you over here was the begin blocks, and then over here it's instantiating a new Perl Critic. So this is all everything it's done instantiating Perl Critic. And then here is the runtime. And then here is document. So we'll be calling this each time it opens a new file. And then here you can see it tokenizing, going into the lexical structure, and then you're all down here in the details. Is this making sense to you?
Is it possible to see which policies might have taken more time to generate?
Probably. Good question. Ask me in a sec. So is that tree map making sense? Yeah. So what you could, another way of looking at it is that the surface area of the tree map is your exclusive time, and it corresponds, sorry, not the tree map, the surface area of the flame graph, kind of the top level. So like here is the Perl regular expression match operator in the lingua en inflect module. And you'll see this crop up again because it's one of the largest exclusive times that was just spent doing that op. And sure enough, it shows up here as the largest time. So it's called 75,000 times. And it'll show up in the tree map. So what should we do? Let's go look at the tree map. So here's the tree map. And here's that core match. So you can say, oh, I spent a lot of time doing regular expressions, and this particular regular expression, or this doing matching in that module. Again, I'm sorry about the colors. They are really bad. Find, so it spent a lot of, find is kind of how Perl Critic, it's the internal document model, and it's chasing around the pointers. So a lot of time spent there. So this is cool, and it's even more cool that you can click on one of these boxes and it'll zoom in to one level down the call tree. So you zoom in again. So you can kind of drill down. So sometimes for these things, you might want to get into some little package down here. So you can click, click, and I don't know, pick a little one down here and click, and click, and click, and click. See, begins. Yep. So it's a way of drilling down. And what you're doing effectively is drilling down into these, you're moving up one of these flame graphs. Is that making sense? Okay. So, subroutines. So if you click on this one, you get a table of all the subroutine calls ordered by their exclusive time. And here you can see that core match. Now you can click on these columns to resort. So here they are sorted by inclusive time. So you can see most of the time is spent kind of right up at the top level. Okay, so now you were asking about whether you can tell which policies take the most time. I would imagine, that although I've not looked, so for example, begin policy, F. So prohibit nested subs, hang on, F. Okay. Yeah, so you can just sort by whatever you want to sort by and search for the policy. Yeah, and that would probably actually sorting by inclusive time would work best. Let's try that. Because then you're seeing what's in the, okay. Yeah, Perl critic policy new, prohibit nested subs, require lexical, etc., etc. Okay. So let's go have a look at some code. So this comes up top, core match, 75,000 calls. If I click on that, it'll take me to, maybe this one's a bit too complex. Let's go back and, this is a nice one, find. So this is where it's traversing the document object model and trying to find things of interest. So up here you see all the places that it's been called, and it was it's called 416 times from all these different places. And you see that each of these is a link, so you can chase up the call tree. So one of the things I use NYTProf for, sometimes if I'm exploring a new bit of code, and I don't care how fast it is, but I'll use NYTProf just to get a sense of how the control flow moves around, because you can drill down and chase up, so that's very cool. And then for each line of code within the function, you can see here we're calling this wanted. Now for this kind of code, it can be really hard to work out, well, what is wanted? Where's it going to go when it does this call? Well, NYTProf will tell you that it's seen that wanted has taken it to all these different places. And again, you can just click on these and click on these and click on these, and you can just hop, 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 hop around the code, which is a lot of fun. It's like making profiling extra fun, which I'll talk about later. How am I doing time-wise? 20 minutes. Okay. Any questions? Oh, come on. I'll start staring at people.
What is the best strategy for jumping into a really big long-running program, jumping into profiling for a part of execution you're interested in, and jumping out in a convenient way?
Okay, so sort of runtime control of profiling. Yeah. You can insert into the program function calls to turn profiling on and off. And then you can start NYTProf with an option set to not be profiling by default. So it'll be loaded, it would have instrumented the code, and then it'll only profile the bits that you asked for. There's a really good Plack middleware, NYTProf something or other, blah, blah, that does this for Plack calls. So you can profile your individual Plack calls, and apparently it's dead cool. Any other questions?
So what are some good strategies for if you have like a multi-threaded or forking in your application, and it generates a million different PIDs to kind of profile, like rather than getting these graphs for each individual PID? Is there any way to kind of put them together?
Great question. Okay, so if you're generating profiles for lots of processes that are the same process but forked, you can generate lots of profile files, and then there's an NYTProf merge that will merge them back together. Now there's a few kind of edge cases. It doesn't work well in all cases. Excuse me, and certainly you'll get complete nonsense if they're not all identical programs. NYTProf does not work well with threads though. In the sense that it'll work, but it'll only profile the top level thread. Yeah. Okay, so this talk is in sort of two halves. One part demonstrating NYTProf, and then another half about just how I go about doing profiling in general. So I think we're about done with that. So go back to the presentation. Okay, demo. Right, let's do another demo. No. Optimizing. Right. Well, I need to turn up the volume because, right. Everything I say here and everything I show you is just one perspective in one circumstance. Always do your own testing on your own Perl binary, on your own hardware. Yep. Do it yourself, because there are so many variables that when you're really after the performance, it's no good using somebody else's data. So also beware the number 2. The number 2 is like really slow. Just don't use the number 2 in your code at all. It'll. I don't know what's going on here. It's crazy. But this is an example where you can easily be led astray, of how easy it is to be led astray. Do you remember I said about the statement profiler? That it's from the start of executing one statement to the start of executing the next. So does anyone know what's going on here? Yeah, so after executing the 2, there's a bit of overhead to get to the next statement, wherever the next statement is, which is probably the 1. But there's a bit of extra overhead, so it makes the 2 look expensive. But always remember, with these timings, it's not just the statement, it's what it took to get to the next statement. Okay, and that's what I just said. Here's another example. 2 identical code refs. Second one's faster. Why is that? Yeah, caching. So your CPU and your memory is all set up and hot after the first call, so the second call runs faster. Yeah, so you'll see this a lot. You'll only really see it with things that are very hot, but it's something to keep in mind if you're really sort of micro-optimizing. You see, in this case, there's like 100,000 calls. Okay. So, before you start profiling, profiling is like the crack cocaine of programming. It's like really addictive, really tempting, and I've just given you a super tool to do it and enjoy doing it. It makes a lot of fun, but the experts at doing these things say the first rule of programming optimization is don't do it. Seriously, don't do it. And the second rule is don't do it yet, and that's for experts only. That Michael Jackson is not the other Michael Jackson. So why not? Why is this so dangerous? Why should you not do it? And this is the reason. As soon as you start thinking about performance, it's so tempting to start breaking all the good rules of how you write good code. And so you start, I don't know. I've seen a lot of stupid things done to trying to make code faster, and often not really succeeding. So you probably heard this quote, Donald Knuth, premature optimization is the root of all evil. But people often forget that the full quote is a little longer, that you should not worry about the small efficiencies 97% of the time, but don't forget the other 3%. There's a time when you actually do need to find why something's slow and trying to make it faster. So how do you do that? Well, again, don't optimize the code. Throw hardware at it, throw memory at it, get a bigger box. All these things are much less risky than fiddling about, trying to get a few microseconds from your code.
That just perpetuates the idea of not having to understand the problem. Like programmers always say, just throw hardware at it. And no one, especially for junior programmers who've never taught assembly code in college, no one's ever taught to actually think about algorithms and how to do things right. Because that's just I find it's just such an easy way to say it. It short circuits the learning process.
It does short-circuit the learning process, certainly. It does mean you're not digging into understanding what's really going on, but it works. It's quick, it's simple. You can sell it to your manager. You can know how long it's going to take to fix the problem. Yeah? You can just buy a bigger box. Now, there's only so often you can pull the buy a bigger box rabbit out of the hat. You know? So I've worked at companies that are growing and growing, and they hit some performance problem, and you scramble around and you pull a performance rabbit out of the hat and say, look, I've made something faster. And then 3 months later, same problem. You know, or it's a different problem, but it's caused by growth. And so you pull another rabbit out of the hat. But eventually you get to the point where there are no more easy rabbits to find. And then because you've put off doing the hard work, you're in a real problem because you're in a crunch and you can't fix it. So yes, you should definitely understand what's really going on, but meanwhile, throw hardware at it. Don't try to second guess. Humans are really bad at working out where performance problems are, even for people who spent a lot of time doing optimization work. You know, they turn up in strange places. And this is an ancient carpenter's maxim: be really sure that you understand where the performance problem is and what the cause is before you change it. So what I tend to do first is go looking for rabbits, low-hanging fruit. I just find some reasonable chunk of work, profile it. I look at the exclusive times. Does anything jump out at me? You know, oh, that looks unreasonable. And usually there'll be something that just looks unreasonable. Fix only simple local problems, and I'll explain that in a sec. Profile again, fast enough, stop. Repeat once or twice maybe, if it's not fast enough, and then move on. Yeah, because you've looked for low-hanging fruit, you haven't found any, move on. What do I mean by simple local fixes? Things that are unlikely to introduce bugs. Now this is one I see a lot. You have a loop, and in the loop there's something being calculated that only needs to be calculated once before you went into the loop. I see it all over the place. This is another one I see all over the place, sort of a lot of repeated chains of accessors. Some of those accessors may be very fast and simple, but some of them might not. Maybe they were fast and simple 6 months ago, but now somebody's added some extra logic. So for these kind of things, you can just use a temporary variable to sort of follow one chain, stick it in a temporary variable, and then for the following accessors, just use that as a starting point. Faster accessors. So this is a little bit out of date, but it used to be that you could just swap in a faster accessor module, assuming you're using these kind of modules to implement your accessors. I think there's one that's accepted now, but at the time I did this slide originally, there was everybody was coming up with a new accessor module.
Moose using one of these, or does it use its own?
Probably. What does Moose use?
Does its own thing.
There you go.
Probably faster than the non-accessible.
Yeah. Okay. Avoid calling subs that don't do anything. Again, I see this a lot of copy and pasted code where people will be calling accessors and banging them into temporary variables, but they're not using that variable. Another common case is logging. It takes time for the logging software to work out that you don't want to log that. Actually, this was a bad example. I should have changed this to be debug, because normally debug's turned off. But if you're calling it, it's taking time to work out that debug level logging is turned off. So usually, logging modules give you some way of saying, am I doing debug level logging? And so you can stick that into a temporary variable and then avoid the overhead of the method call and the logic. Use preconditions, cheap tests to see if you should be doing anything in this subroutine. Usually methods have a bunch of initializations and then some checks. Those initializations may be expensive. You may be calling accessors. And then you decide that the subroutine or the method doesn't do anything in return. Swap it around, do a few basic tests, save work you don't need to do, or avoid work you don't need to do. This is an actual diff from some code that I was optimizing. There were lots of examples like this. So just, people who aren't familiar with the way Perl works or who are just smoking crack, that kind of thing's simple. Sometimes regular expressions can be time-sucking things. Doesn't happen very often, tends to be particular use cases, sort of complex regular expressions. But NYTProf now shows you the time spent in regular expressions, so it isn't as big an issue as it used to be. Avoid unpacking args in very hot subs. It's surprising what a difference this can make in a very hot sub if you've got something that's being called a lot. Typical case is a delegation or an accessor. Another one I see quite often, regular expressions that have parens, where the parens are being used for grouping, but the parens trigger the capture of that string, but it's not actually used. There you can just put a question mark colon after the beginning of the paren to turn it into a non-capturing paren. Okay, so you've gone through, you've found these things, you've fixed them up, you retest. Is it fast enough? Not as fast as it could be, but is it fast enough? And if it is, you stop, put the profiler down, walk away. But if you think you still need to go further, then you can get into more deeper stuff. How am I doing time-wise? Okay, we're grand. So what I do here is I give the code some known workload. And the typical example would be a web service. And I'd fire like 1,000 identical requests. And there's 1,000, and they're identical. And that's like a known workload. And that helps me reason about the timings and the numbers. So what I then do is I look at the call counts. And I say, OK, well, I gave you 1,000 identical requests. Why is this method being called 10,000 times? Yeah? Because at those kind of things, often you'll say, well, I only need to call that once. Sorry, once per request. Yeah? And so by knowing the exact number of counts, by knowing the nature of the workload you've given it, then unreasonable counts will jump out. And usually that's a case where you say, oh, if I've given it 10,000 identical requests, I could use caching. Yeah, for those 10,000 requests, it should only call something once because it should be cached. So it shows opportunities for caching, and it exposes where caching isn't working, but you expect it to. And then the next thing I do is look at the top level inclusive times. This sort of load, process, write out. Where is the division of time? Am I spending sort of 10% loading, 80% manipulating, 10% output? Or is the output really slow for some reason? Or is the input really slow for some reason? Is the balance reasonable? And again, having a known workload lets you reason about these things. Add caching. There's an old saying that the two hardest problems in computer science are naming things and cache invalidation. Off by one errors, yes, thank you. So caching is a really good solution to many of these things. And in fact, some of the things I've already mentioned, like getting rid of repeated accessor chains by using a temporary variable, that's a kind of caching. But it's really important, whenever you're tempted to add caching to a program to make it faster, you should have a red flag waving around inside your head saying, how am I going to invalidate this? At what point is this cache data going to cease to be valid, and how am I going to deal with that? That call chain chasing you can do within NYTProf that I showed you, where you can call up to see where something's being called, and you can chase up the call tree. It's a great way of finding a good spot for caching and for cache invalidation, and it'll tell you whether there are multiple callers in to something. Because if there are multiple callers in, if you put caching in just one of the callers, then that won't affect the others. Yeah. So you might want to add, for example, an extra layer of indirection that just adds the cache wrapper to the original method. Okay, another common example I've seen is creating heavyweight objects in one part of the code that then aren't actually used. So a classic example here would be processing log files. You're processing log files that have timestamps, and you create date-time objects for every single record as they're being loaded. But then you throw most of them away, because you're only looking at a few. So a good solution here would be something like a lightweight proxy. And there was a case where in some production system, I made a massive improvement by doing something very like this. And there are three of them. It's an old slide, so there might be different ones now. Dave, do you? No? Yeah. So look out for this kind of thing, where you're doing a chunk of work that makes perfect sense, like using a datetime object when you're loading, but actually later on in the control flow, you don't use the object that you spent time creating. Reconfigure your Perl. This is an interesting one. The thread support, the cost of using a Perl that supports threads, it has some cost, and it varies a lot between platforms. The figure I have here is 2 to 30. I don't know. Bulk, do you want to make a guess at the cost of a threaded Perl versus non-threaded?
Me?
Yeah, come on.
I've never benchmarked it.
What? I'm surprised. I picked you because I figured you would. What I'm told is between 3 and 20, depending on the platform. I think for Linux, it might be sort of 5 to 10. If you don't need threading, you could get a faster Perl by building a Perl that doesn't support threads. Never run in production with a Perl that supports debugging, because it's a significant cost, 15%. But there's a lot of other tuning about the particular malloc, whether you use 64-bit ints, long doubles, optimization. Disabling taint mode is an interesting one. The newer versions of Perl, you can disable taint mode at configure time. And I've heard reports of like a 10% performance boost, which is surprising. But there you go. If you're not using taint mode, that's like 10% that's just available to you.
What about multiplicity? That's always been a question mark for me.
Multiplicity. So multiplicity is part of the way Perl supports threads. It allows multiple Perl interpreters to coexist within a process, which is then a foundation for running threads. But multiplicity is used by things like Postgres to allow multiple interpreters. Does it use? Actually, no. I think I'm lying there. But anyway, there is some overhead in multiplicity, but not as much as threads. But I don't know what it is.
If I get rid of threads, do I need?
It might. Sorry.
If I get rid of threads, do I need multiplicity?
You can build, if you have threads, you have to have multiplicity. You can have multiplicity without threads.
Multiplicity is the token that was used for 5005 threads. It eventually became thread support when 5005 threads were removed, but the token still lives to this day. Just to mean that we can have multiple interpreters in the same process. So thread support is, do you have iThreads, or can you have multiple interpreters for embedding? Because iThreads uses the Perl interpreter embedding stuff to
Right.
create multiple iThreads on a pure Perl level.
Okay.
So multiplicity is threading support.
Okay. I disagree, but I could easily be wrong. So bulk is more likely to be right. Another option is to use a different compiler. So GCC versus CLang versus Intel compilers. You know, if you're in a business and you can afford a commercial compiler license, try using that. Upgrade your Perl. Perl is getting faster. Through 5.8 to 5.20, every release has got faster, sometimes significantly faster, and often using less memory. Now, sometimes certain little things get slower, but generally, newer Perl's faster using less memory. A lot of work has been done in recent years. How much time do I have?
8 minutes.
8 minutes. Okay. Grand. We're doing good. I'm racing along. Retest. Is it fast enough? If it is, stop, put the profiler down, walk away. Now we're going to do sort of deeper stuff. We're going to sort of get out the hatchet and start chopping things around. Simple one I've used to good effect often is to push down data structures. You'll often be doing this kind of thing where you're calling a method on a sequence of values. If you can add a method to the class and you just hand it all the values and say, go do that. So if that walk method, for example, was doing checks to see whether you were somebody who was allowed to walk the dog, assuming it is dogs, yes. The walk these method could just do that check once. If you're calling the walk method over and over again, it's having to recheck if you're a valid person to walk the dogs. Yeah. So that's a very simple kind of change that often yields good benefits. Faster modules. There's a nice module called sort key for building complex sorts. Storable is grand, but serial is much better. If you're doing data serialization, take a look at serial. LWP is full-featured and rich, but it's also old and slow. For simple things, HTTP tiny, tiny light, curl, hijack. I don't know how you pronounce that. But there are variations that have less functionality but are more focused on speed. And so, you know, those can be easy changes. Deeper things, you might be using hashes where arrays would suit better, or maybe you're using arrays where hashes would suit better. That's kind of more structural changes. Sometimes just the whole approach to the way you're trying to do what you're doing isn't the best way of doing it. So you could look at whether the whole approach that part of your program is taking is the best approach. I've had success with this in a few cases where I've optimized something to the nth degree in Perl, but it was relatively simple logic, and I've replaced it with a chunk of C code. Inline C is a good way of doing that. Inline C, when you first run the code, when you first load the module, it fires up a compiler in the background and loads the generated object dynamically. So it's a bit weird in terms of deployment. You have to have a compiler at the place you're deploying to. But it's a very neat way of providing either a Perl or C version. And finally, if you've done all these things, and you're profiling the code and nothing is jumping out at you, don't worry, still keep making little changes, because all the little changes that don't seem very significant by themselves add up. So you can still make good progress. Parent, you get a name check here for this presentation. What I've been talking about has been sort of very generic. Parent's presentation there talks about some specifics. Any questions?
Would you recommend not to use recursive functions?
Sorry?
Not to use recursive functions?
Do I recommend not using recursive functions? No. Recursion is cheap. You know, and if it's the best algorithm for what you're trying to do, then fine. Yeah.
Have you spent too much time profiling NYTProf? Repeat the question, please.
Yeah. Have I spent too much time profiling NYTProf? No is probably the right answer. The guts of NYTProf are all written in C, which makes profiling a bit tricky. And I probably haven't spent enough time profiling the report generator. I've done some, but I could do more. So patch is welcome. Yeah. Any more questions?
Just one comment I'd add about using C and XS versus Perl. One of the things I found that Perl can not be so great with is when you're doing just a lot of data processing or building large structures, it allocates so much memory so frequently that can just slow things down. And switching to XS and being able to switch from, say, a Perl hash to a C struct can just save you a ton of memory allocations.
Yeah. So I'll just repeat what you said. The Perl is very generous in its use of memory, to put it mildly. Now, it's generous in the use of memory in the interests of being efficient in some respects. But if you're building a lot of data structures, that inefficiency in terms of memory usage adds up fast. And then you can get performance problems simply because you're allocating so much memory, the impact on the system is bigger. So you were recommending C as a great way of doing that, and that's true. But a pure Perl twist would be to say, well, if you're loading a lot of things, you might be tempted to use a hash, where actually if it's all sort of the same shape, you could use an array. Yeah, so there have been cases where I've been loading a lot of things that were hashes that may have 5 elements and they're all the same. So I turn that into loading them as arrays. And there's a big boost there. Arrays are much cheaper than hashes. More questions?
Are these slides online?
Yep, the slides are last year's version of this talk. Slides are online, and I'll upload this this afternoon. You'll find them on SlideShare and linked from the talk page. But you can just Google NYTProf Tim Bunce slides. Any questions?
What do you think of the advice, I believe it was from Kernahan and Pike, practice programming, to measure the amount of time that the programmer will spend optimizing versus the time saved across the run of the program?
Yes. Yes. So repeat the question. I spoke earlier about the need to sort of measure twice, cut once. Be sure of what you're doing. But obviously, it's taking you time to do the profiling, and you could spend a lot of time doing profiling. And there comes a point where the gains you're likely to get from the profiling are less than the time you're spending doing the profiling. And at that point, you should definitely put it down, walk away. Your job is done. Because unless you're spending your own time, if you're spending company time, then you're costing the company money just trying to look to save time. So, yeah, it's a good thing to keep in mind. Okay, last question. Come on, gotta have something. What's for dinner? Okay. We're hiring, thank you. We are hiring. Yay. No. Okay. Yay. There we are. Yes. We're hiring. Come and talk to me. Okay.